Welcome back. This is section 27.3, Induction and Energy. If you move a magnet toward a wire loop, as we discussed in the previous video, you get an induced current. With the induced current, the wire heats up slightly because it has resistance, and that resistance dissipates energy. So you get heating from it. And the source of that energy is mechanical work that you do when you originally move the magnet toward the wire loop. Now I want you to imagine, you look at the picture, a very, very long coil. And we take a magnet and we shove it through, and the magnet can move in such a way that it doesn't touch the coil, and there's no friction, there's no atmospheric resistance. We just give it a little shove, and by Newton's first law, it'll just keep on going in that direction. So the magnet coasts on through. Now, as it coasts on through, there is going to be heating, but then the question is there going to be infinite heating from a little shove that we give it as it approaches more and more coils and leaves more coils behind? Can we get infinite heating? And there's something that doesn't sound right about that we could get infinite heating from just a little shove of the coil. And of course, the answer is no, we cannot get infinite heating as it slides through this very, very long coil. And the reason is that mechanical work is needed, not just to get it initially going, but to keep it moving. Now you think about Newton's first law. Newton's first law says you don't generally need mechanical work to keep something going, but here you do because there is something resisting its motion. And this is an important concept here with induced currents. The induced current always has a magnetic field that opposes the change in the magnetic flux. What we're going to see is that this is what acts like the things I said originally in this example to get rid of. Let's say there's no friction, no atmospheric resistance. Well, the induced current is going to oppose that change in magnetic flux. And this is the meaning behind the negative sign when we have the equation that the induced electromagnetic force is the negative of the change in flux over change in time, that rate of change. That's the notion of that negative sign. Now, I told you when I introduced to you Faraday's law that we won't be using that negative sign. In fact, in this class, and for these problems that you'll be getting, I just ignore the negative sign, but that is the nature of that negative sign. And that negative sign itself can be thought of as Lenz's law, which says that the direction of an induced EMF or current is such that the magnetic field created by the induced current opposes the change in magnetic flux that created the current. Now, for example, let's take this wire loop, and we've got a magnet. We're going to move the magnet towards it, and you can see the direction of my magnetic field lines. They come from the North Pole, and I'm not drawing the rest of the field lines for this picture. You know, they curl back around towards the south, but we're interested here in the magnetic field lines that go through the loop. Now, as we move the magnet towards the loop, the magnetic field in the loop is going to get stronger because it's stronger as you get closer to the North Pole, which means the flux is going to increase. So as we look at this motion of the magnetic field pointing to the right and the flux is increasing. So there will be an induced current, as you learned in the previous section, but now we're going to talk about the direction of that current. The current induced will have a magnetic field that opposes that increase. So what we're going to do is use a right-hand rule, and we're going to think about if the magnetic flux is increasing to the right, we're going to think about a current through the loop that's going to push back in the opposite direction, meaning using my right-hand rule and curling my fingers in the direction, let me back up. Using the right-hand rule and pointing my thumb in the direction that pushes back against the magnetic field that's increasing. My fingers will curl in the direction of the current. So there you see in the picture, my fingers curling in the direction of the current. We'll go through a few other examples. Now let's take that same magnet and we're going to pull it out, move it to the left. Well, in that case, you see the magnetic field lines and they will be decreasing. So if the magnetic flux pointing to the right is decreasing, we're going to take our right hand and point our thumb in the direction to the right. It's decreasing to the right, so we want to increase it. We want to think about shoving with our thumb more magnetic flux to the right. So I point my thumb to the right as if to stop it from decreasing, the magnetic flux from decreasing, and you see my fingers point in the direction of the induced current. Now we don't have to move the magnet at all. For this example, you can see the picture. What if the ring grows in size? And it doesn't have to stay as a circle. It could just be reshaped to just have a greater area. So in that case, magnetic field lines go to the right. If it increases in size, that means there's more magnetic flux. So the magnetic flux to the right is increasing. We're going to use our right hand and point with our thumb to oppose that increase. We're going to push back to the left as if to decrease the magnetic flux. And there we have my fingers in the picture showing the direction of the current. Let's look at this picture. Here we have magnetic field lines that are pointing into the page. And we're going to rotate the ring. You can see the axis, the vertical axis. Now, as that ring rotates, you can think of it as the angle changing. And you know that the induced or the flux equation deals with an angle. But maybe it's easier visually just to imagine that the area that the magnetic field lines are going through is decreasing. And so with that decreasing area that the flux lines are going through, you have a decreasing flux. So we think, what direction is that going to be? Well, magnetic field is going into the page and the flux is decreasing. So we are going to take our thumb and push more into the page to try to stop that flux from decreasing. It's as if our thumb is adding magnetic field in that direction. So we're going to point our thumb into the page with our right hand, and there you see the current is going to go in the direction of the fingers of the right hand, so clockwise. Let's take this next example. We have a current in the wire on the left, and it's going straight up vertically, and a loop to the right. And I've put a non-symmetric shape just to show you it doesn't matter what shape the loop is, as long as it's a closed loop of conducting material. Now, I've already drawn in the magnetic field, but I want you to think which way, convince yourself that this is what the magnetic field looks like. So to see the direction the magnetic field looks like that is being produced by the wire, that's the right-hand rule, where we pretend to grab the wire with our right hand, thumb is going in the direction of positive current, and your fingers on the right-hand side of that wire should curl into the page. Not that I've drawn it, but on the left-hand side, they would curl out of the page. Also remember that as you get farther away from the wire, the magnetic field decreases in proportion to the distance. And so there's where I've written at the top, it's a strong magnetic field near the wire. It's a weaker magnetic field away from the wire. Now we're just going to move that loop in the direction that I've drawn. So in moving the loop in that direction to the right, we are decreasing the flux. It's keeping the same area, it's keeping the same angle, but the magnetic field in the loop is decreasing. So the magnetic field going into the page, and it's decreasing. So we're going to take our thumb with our right hand and push more into the page. And so we see that the the current is going to go around in the clockwise direction. Now we can do the same example. Now move the loop back towards the wire, and here we're moving it into a stronger magnetic field. So I consider the magnetic field going into the page, but now it's increasing. And so I'm going to take my thumb and point it out of the page to try to push back against that increase. And so we get the induced current going counterclockwise. Let's look at a previous example that we did in the last lecture, example 27.4, where you have two parallel conducting rails, a distance L apart, connected at one end by a resistor, and there's a bar that's going to slide along that rail. And in that problem, we calculated what the change in flux, or what the flux is, and then the rate of change of the flux, and we figured out the current. But now I want to look back at it and think, what is the direction of it? So there we have it. You see the v velocity vector that shows we're pulling the bar to the right. As the bar is pulled to the right, the magnetic flux increases into the page. So the induced current around that loop will have a magnetic field that goes out of the page. So flux is going into the page. We're going to take our thumb and point it out of the page. And so we can see that the current is going around counterclockwise. So in that example, the rod moves with the speed v, and it travels some distance, we'll call it delta x. You can see my drawing right here, delta x. In some time, delta t, so we'll say delta x is v delta t. Now the loop area, this area that's increasing, we're going to call the change in that area delta a, and that is the length L times delta x. And I want to relate this to the current, the induced current, the induced electromotive force, and see what we come up with. So Faraday's law is that the electromotive force is negative delta phi over delta t. Now I'm going to replace delta phi with delta BA, but B isn't changing, so let's put B out to the side. So negative B delta A over delta T. For this derivation, I'm just going to leave the negative sign in there. Now we have negative B, and then I'm going to replace delta A with L delta X, what I wrote up here. And remember, delta x is v delta t, so that numerator becomes negative b lv delta t, but then divided by delta t. So the electromotive force in volts becomes negative b lv. So that means the magnetic field times that length times the speed that we're pulling on the bar. Now remember that a current in a magnetic field experiences a force. The bar will experience a force, and that's going to be to the left. And why I say to the left, we'll look at a little picture I have right here. The bar V, so it's got a current that's going up, and we know that because we already figured out by the right-hand rule the current, the induced current, is going counterclockwise. So in the bar, that current is going up. It's in a magnetic field that points into the page. And so one of the first right-hand rules you used to figure out what force does a current feel when it's in a magnetic field, I place my outstretched hand pointing straight up, my fingers curl into the page, and my thumb points to the left. So that bar that we are pulling to the right is experiencing a force to the left. Now, the force that it feels is ILB. Remember, current times the length of that bar times the magnetic field. And let's replace the current with the electromotive force, which is BLV. I found that in the last page, divided by resistance. And so the force that that bar feels pulling back to the left is BLV over R times LB. Putting all that together more concisely, we can say that the force that the bar feels, that pullback that it feels, is B squared L squared V over R. And notice that it's proportional to the speed. And that's kind of like air resistance is proportional to speed. So the faster we pull on that bar, the more resisting force we're going to feel. Now, the rate of energy dissipation through that bar, from that bar, is power equals current times the electromotive force. And that current is BLV over R. The electromotive force is BLV. And so there is a rate of energy dissipation measured in watts because it's power, B squared L squared V squared over R. And there I've written that again from the previous page. Now let's think back to the mechanical effort that we're putting in to grab that bar and pull it to the right. If we are mechanically applying that force to maintain a constant V, then, and this is something we did in first semester, power equals force times velocity. And the force is B squared L squared V over R times V, and that becomes B squared L squared V squared over R. The whole point of all this is, look at these two equations that I have in the boxes. We are getting heating from the bar, rate of energy dissipation. And that energy is not for free. It has to come from somewhere. It comes from the mechanical work that we have to apply in order to move that bar, which is what induces the current to get that heat, that energy dissipation. And that's the mechanical power, which is exactly the same. Let's look at an application of electromagnetic induction. And this is on page 473 of the book, and you can see a picture of a generator. You can read about a generator. The idea behind a generator is that mechanical energy rotates a loop that's in a uniform magnetic field. Now, I've got down at the bottom, my drawing is a little bit different. In this case, it's a loop that's sitting still and the magnet itself is rotating. But the point is, through some rotation, you have a changing magnetic flux, a continuously changing magnetic flux through the loop. So remember that flux is BA times cosine theta. And with that changing cosine theta, there is a continuous induced electromotive force. Now, the sources of mechanical energy for a generator, it can come from steam. And down below, I draw a steam turbine. And in our electrical power plants, where electricity is produced, that steam will come from maybe burning of fossil fuels. It might come from nuclear power. It can come from wind or water power. But we need some source of mechanical energy in order to get that loop and or the magnet rotating with reference to each other. The direction of the current is going to switch with every 180-degree rotation, and this leads to alternating current, which is a current that goes back and forth that's continuously switching direction. So you think back to this picture, and I showed this in an earlier chapter on thermodynamics. You have a steam turbine, and with high temperature and pressure steam on one side, low temperature and pressure steam on the other side, it gets spinning. And then we attach a magnet to that. So now as it's spinning, you've got this continuously changing magnetic field. And now I've drawn a loop over to the side, and that loop is going to be connected to a circuit that ultimately brings this electricity to cities and houses and buildings. But in this simple picture here, you can see as that magnet rotates, you're going to get a continuously changing flux through the loop, and that's going to lead to alternating current. Another application is transformers. Here we have an iron core, and there are two electrical circuits. One is on the left, the primary, and the second is the secondary. And on the primary, it's looped around several times. And on the secondary, it is looped around some other number of times. Now, I've drawn the secondary having more loops than the primary. It doesn't have to be like that. But for a transformer to be effective in ways that I will explain, you'll see that they should be a different number of coils. In the primary coil, we have an alternating current. So this is a changing current that results in a changing magnetic flux through the secondary coil. And this induces an EMF in the secondary coil. The induced EMF then drives a current in any circuit that's connected across the secondary. So this device transfers electric power between two circuits without direct electrical contact. Now let's look at this picture. Imagine you have a changing EMF, so a changing current, and remember that any wire with a current in it produces a magnetic field. Well, if that's continuously changing, if the current is continuously changing, then its magnetic field is continuously changing. Now hop on over to the right. You then have a continuously changing magnetic field through this loop, and that's going to lead to a continuously changing induced current. Notice also that they are not in direct electrical contact with each other. We have a circuit with a wire, another circuit with a wire. They are not actually in electrical contact with each other. You notice the symbol that's drawn here. There's the loop, and then a break in between them. But it is important to note that there's no direct electrical contact between these two circuits. So the alternating current that comes in from the left, you can see its graph right here, current versus time. And so as I wrote here, the changing current, I'll call it I1, leads to a changing flux through the secondary, and that leads to an induced current that I'll call I2. Therefore, electric power transfers between the two circuits. Now, there are two kinds of transformers. One is a step-up transformer, where the peak voltage gets increased, going from the primary to the secondary. You get an increase in voltage. And then a step-down transformer is where the peak voltage is decreased. And I say peak voltage because with direct contact, direct current, DC, you just have a voltage coming from maybe a battery. But in this case, it's got a sine curve to it. So just as I've drawn here that the current is in a sine curve, the voltage is also. So we talk about the peak voltage. The relationship between those two voltages is V2, so that's the peak voltage of the secondary circuit, is the ratio of the coils, N2 over N1 times V1. Now the picture that I've drawn has more coils around the secondary, and so that is a step-up transformer. So step up just means N2 is going to be greater than N1. If N2 is less than N1, it's a step down transformer. So a simple example, an AC adapter for a gadget that uses maybe 9 volts, but it pulls in power from the wall socket and it gets 120 volts in an electrical outlet. So it's taking 120 volts, but it only needs 9 volts. So we need a step-down transformer, and that's why AC adapters are often pretty bulky. There's this transformer in there. Well, 120 volts to 9 volts, that's a 40-to-3 ratio, which means this can be achieved if the number of coils around the primary is 40 and the number of coils around the secondary is 3. And so the equation then shows that 9 volts equals 3 over 40 times 120 volts. Here we have, I know the writing's a little small, but just an idea of how we get power from the power company all the way to our houses. It uses a series of transformers. So typical amounts from the power company, it's 20,000 volts. Transformers change the voltage levels throughout the power distribution network. By the time it gets to our house, it's only 240 volts. Well, what happens, you've got a transformer as it goes from the power company to the cities, and it gets turned to 365 kilovolts. And then at some points, distribution line in the city is maybe 4,000 volts, and then it breaks up to the various neighborhoods and on into the houses, and it's 240 volts. Let's now look at some practice problems. Let's start with number 32. It says a conducting loop of area A and resistance R lies at right angles to a spatially uniform magnetic field. Now, spatially uniform means that at a given snapshot in time, it's all going to be the same, but it's going to be changing in time. At time t equals 0, the magnetic field and loop current are both 0. Subsequently, the current increases according to I equals B times t squared, where B is a constant with units amperes per second squared. Find an expression for the magnetic field strength as a function of time. All right, so there's the picture. I've drawn in the direction of the induced current. Not that it asked about that, but let's just think about that. We're going to take our right hand, and if it says that it's going into the page and it's increasing, we're going to take our thumb and shove back in the opposite direction to try to keep that flux from increasing. And so we get the direction as I've drawn in the picture, counterclockwise. But let's get to the quantitative analysis here. We know that the electromotive force is current times resistance, and the electromotive force is d phi over dt. And here you can see, as I usually do, I've just dropped the negative sign because I'm interested more in magnitudes. Well, that means that current times R equals d dt of AB. Area is not changing, so let's move A out to the side. So we get current times resistance is area times dB dt. Let's replace current with what it says, little b times t squared times R. And that equals, on the right-hand side, A times dB dt. And the question is asking to find an expression for the magnetic field strength as a function of time. So we're looking to solve for big B. And as a function of time, well, we've got this combination of t, but also dt, so that tells us calculus is going to be involved. And what we're going to do is take this equation where my pointer is at and move everything that's not magnetic field over to the left-hand side. So little b t squared times r, let's get that dt over there, let's divide by a, and we're left on the right-hand side with the integral of dB. Let's integrate both sides of the equation. Integral of dB, that's just b, what we're solving for, and then we integrate the other side of the equation. Little b, r, and a, they go out to the left, and we end up taking the integral of t squared dt. And we're taking it with the limits of integration from 0 all the way up to whatever time t, so we'll call that t as well. And in the end, we get magnetic field is little b times resistance times t cubed over 3a. Let's look at number 33. You can see my picture there to the right. It says a conducting loop with area 0.15 meters squared and resistance 6 ohms lies in the XY plane. A spatially uniform magnetic field points in the Z direction. The field varies with time according to B sub Z, so the Z component of magnetic field equals AT squared minus B, where A equals 2 Tesla per second squared, and little b is 8 Teslas. Find the loop current at time 3 seconds, and when the magnetic field in the Z direction is 0. So here I've drawn it according to what it says in the book. Magnetic field, it says it's pointing in the Z direction, and so we can say magnetic field is BZ times K hat. It also says that BZ is AT squared minus little b, and that is 2T squared minus 8. All right, so let's figure all this out. Let's look at part A. The induced electromotive force is d phi dt, which is in the numerator the change in A times B, but A isn't changing. Let's throw it out to the left. And so we have A times dB dt. And when we take the time derivative of magnetic field, well, here's the magnetic field over here to the right. So 2t squared minus 8, take the time derivative, that just becomes 4t. So that the electromotive force is the area, 0.15 meters squared, times 4 times, and here it says at time equals 3, so 3 seconds, and we get 1.8 volts. Therefore, the current is electromotive force divided by resistance. So the 1.8 volts divided by 6 ohms, and we get 0.30 amperes. The second question asks to find the current when the magnetic field in the Z direction is 0. Well, up here to the right, it gives the equation for magnetic field, the Z component, 2t squared minus 8. So let's solve for when that's 0. 0 equals 2t squared minus 8, and then time equals 2 seconds. That's the time it happens. Now we want to find the current. The electromotive force is, now we already found this, come up here, right where my pointer is. We've already solved for that electromotive force is area times 4 times whatever the time is. Now we're using a time of 2 seconds. So we plug it in there and we get 1.2 volts, so that the current is 1.2 volts over the resistance of 6 ohms, and we get 0.2 amperes. And there's the direction of the current. And you can do that for yourself and see, convince yourself that the current does indeed go in that direction. Let's look at number 36. A magnetic field is given by B naught times x over x naught squared, k hat, where B naught and x naught are constants. Find an expression for the magnetic flux through a square of side 2x naught that lies in the xy plane with one corner at the origin and sides coinciding with the positive x and y axes. I've drawn a picture right there, and going through what the problem says in the book, it says the magnetic field is in the k hat direction. So there I've drawn it coming out of the page properly in the z direction. And we want to find the flux. So flux is B times A times cosine theta. However, in this case, those components are changing. So B is changing. And so we can't just simply use BA cosine theta. When any of those components are changing, we have to go to this equation using calculus and find that the flux is the integral of B dotted with dA, which in this case is going to be the integral of BdA. Now let's do that. So the integral, let's take our limits of integration as As we break down A, well, first let's actually look at the picture right here to see the nature of this dA. We're going to break the square into these little strips of width dx. So the little area of that strip, which is dA, is going to be 2x naught, which is the height of the strip, times dx. So let's break down that dA into, right here, 2x naught times dx. And now what we're doing is we're integrating, instead of over dA, we're doing it over dx. So we have the integral, you look where my marker is, of b times 2x naught dx. And since we're integrating over the variable x, we're going to go as far as the square goes on the x-axis. So it starts at 0 and it goes to 2x naught, and those are the limits of integration. Now let's go through this. We can see b, you go up to the original equation for b. b is b naught times x over x naught squared, so I've done that here. I've called it x squared over x naught squared. And then still times 2x naught dx. We simplify that and move everything that's constant over to the left of the integral, so we get 2b naught over x naught going out to the side. And we're left on the inside of the integral with x squared dx. So we're going to take that integral, and it becomes 1/3 x cubed. I've moved the 1/3 out to the side. Integrating x cubed from 0 to 2x naught, that becomes 8x naught cubed. And we simplify all that, and we end up getting that the flux is 16/3 times b naught x naught squared times Tesla's meters squared. That is the end of section 3. Have a great day.